Right. So last class we discussed some applications of the formula of magnetic field produced by a straight current carrying wire. The next thing we are going to discuss is Ampere's law. Consider a straight current carrying wire like this. Assume it is infinitely long. Okay. Let's say the current in it is flowing in the upward direction. Can one of you quickly tell me the shape of magnetic field lines produced by a straight infinitely long current carrying wire? Shape of the magnetic field lines.
Circular loops.
Circular loops, okay, whose centers fall on this line itself. Okay, so you can imagine one magnetic field line like this around this current carrying wire. Half of it, half the field line will be out of your screen and half of it will be behind. And since the current is flowing in the upward direction, place your right hand thumb in the upward direction and curl your fingers. You can see the direction. You can visualize the direction of the magnetic field. So the magnetic field is directed like this. And as we discussed in the last class or the class before that, magnetic field lines always form closed loops. Okay. So over here, the field is into the screen, and over here, the field is out of the screen. Okay. Assume this loop, this circular loop, has a radius x. So basically, all these are points which are at a distance x from the wire in a plane perpendicular to the wire. Okay. It's like if you consider the wire to be along the y-axis, the circular magnetic field line is in the xz plane. Okay. Fine. Now, one of you quickly tell me, what is the formula for magnetic field produced by an infinite straight wire at a distance x from it?
Mu naught by 4 pi 2i by x.
Mu naught I by 2 pi x. Okay, 2i by x you said. Why did you say it that way? You said mu naught by 4 pi 2i by x.
Sir, I learned this concept from a YouTube video. Someone shot in that.
Okay,
They
fine.
said some tricks based on that.
Okay, no problem. Fine. Okay, it's all based on mu naught I by 4 pi x into cos theta 1 plus cos theta 2. Yeah, it becomes 2 and 2i and 2 gets cancelled. You get this. Okay, now we have clearly drawn the magnetic field line. So we know the direction of magnetic field all along that line. Now consider a point on that magnetic field line and move a small distance, okay, say dl along the field line. So at that point, the magnetic field and the small displacement dl are in the same direction. Fine. Then in that small displacement, dl, if you do b dot dl, if you simply take the dot product between the magnetic field and that displacement vector. Okay. One of you tell me, what is the general formula for A dot B?
AB cos theta.
AB cos theta. So here it becomes B dl cos theta. In this case, theta is 0. Because we have chosen to move along the magnetic field line. Okay, so the angle between the displacement and magnetic field will be 0. Cos 0 becomes 1. So the dot product simply becomes B dl. Okay. So B here is mu naught I by 2 pi x. dl is dl itself. Let's keep it as it is. Okay. Now, if you continue undergoing that displacement along the field line itself, okay, and you integrate all the B dot dl terms. Now, keep in mind, I am telling you that we are moving along the field line. So if we are moving along the field line, at every instant, the angle between the B vector and the dl vector will be 0 itself. We are intentionally moving that way. Okay. So dls are like this. So everywhere the angle between B and dl is 0 itself. So everywhere B dot dl simply becomes B dl, which is mu naught I by 2 pi x into dl. Okay. So if you integrate this, you'll effectively be integrating mu naught I dl divided by 2 pi x. Mu naught I 2 pi x. These are all constants. Okay. X is the radius of the circular loop along which we are moving. Okay. We have fixed that radius. So it's a constant. It doesn't change from element to element. Okay. All you need to do is, all you're left with is integral dl. And it's not even integral dl vector. It's just integral of the magnitude of dl. So if you integrate all the dls, can one of you tell me how much it becomes? Just integrate the lengths of all those small elements, small displacements. How much does it become?
2 pi r.
In
Like
this
2
case, it is
pi
2
x.
pi x. Correct. 2 pi x. And you will effectively be left with mu naught I. Okay. And since we have done the integral over this magnetic field line, we know magnetic field lines are closed loops. So effectively what we are doing is we are integrating over a closed path. So we call it as a closed integral B dot dl. And what do you get? You get mu naught into I. Now we have taken a very convenient case. We have taken a straight infinite wire and we are intentionally moving along the magnetic field. Okay, so we got this result, integral closed integral B dot dl is equal to mu naught I, where I, as you can see, is the current passing through this loop. It's going from one side of the loop to the other side. Okay, so you call that as the current enclosed by this loop. Fine. So as I said, we have taken a convenient case and derived this result, but this result is true in general. Okay, so you don't need to take only a straight infinite wire. Whatever be the system producing the magnetic fields, if you do integral B dot dl over a closed path, okay, in fact I should say if you integrate the net magnetic field over a closed path with respect to length, it will be equal to mu naught into I enclosed. Fine. This is what we call as Ampere's law. Fine. You can say this is kind of analogous to Gauss law in electrostatics. Can one of you tell the formula for Gauss law or mathematical form of Gauss law?
Closed integral E dot dA is equal to Q enclosed by epsilon.
Right. Closed integral E dot dA. That's basically net electric flux through a closed surface, okay, is equal to charge enclosed divided by epsilon naught. Now see, in electrostatics, this term closed integral E dot dA had a meaning. It's called electric flux. Okay. In magnetism, this term closed integral B dot dl, as far as your syllabus is concerned, +1 +2, this does not have any meaning. We just call it as the line integral of magnetic field over a closed path. Okay, there's no separate name for it. We just call it as line integral of magnetic field, and that will be equal to mu naught into I enclosed. Okay. And see, there's a condition here. Now in this case, conveniently, we took the dl vectors along the direction of the magnetic field, right? Suppose you decide to move opposite to the magnetic field. along that field line itself, but opposite to it. If you take dl vectors like this, you will still be going in a closed path. Okay. But can one of you tell me what the result will be if you go in the reverse direction along the magnetic field? Will it still be mu naught I, or will it be any different? This usually they ignore this point in books, but you should be able to comment on it. You look at the derivation. Only thing I'm changing is the direction of dl. Field remains the same, but the way we are moving is changed. We are moving in the opposite sense now. Will the result be the same? That's my question. Yash, what do you say?
Sir, we are moving in opposite of the magnetic field.
Yes, we are moving opposite to the magnetic field. So will the end result still be mu naught I, or will it be anything else? Isha, any comment? Yashmit, any answer? Okay. Listen, the current is the same, so the magnetic field it produces will be the same. That we cannot change. The way we move along the closed loop is in our hands. Okay, they should either specify in the question, or it will be in our hands. It is our choice. Now in this derivation, we moved along the magnetic field and we got mu naught into I enclosed. If you move in the opposite direction, no, you will see a change here in the dot product. If you are moving in the opposite direction, observe those yellow vectors. They are opposite to the magnetic field. So if you move in the other direction, other sense along that loop, the angle between magnetic field and dl vector everywhere, how much will it be? If you move as indicated by the orange arrows, angle between B and DL is 0. If you move as indicated by the yellow arrows, what is the angle between B and DL everywhere?
It will be 180 degrees, sir.
It will be 180 degrees. And what is cos 180?
Minus 1, sir.
Minus 1. Then you will get a minus, you will take minus 1 here. Then you will get a minus sign here. You will get a minus sign here. And then you adjust everything. Finally, also you will be getting a minus sign. Okay. So the integral, the closed integral B dot dl is actually plus or minus mu naught into I enclosed, depending on the way you move along the loop. Okay, so remember it this way from now onwards. Closed integral B dot dl is equal to plus or minus mu naught I enclosed. Fine. The same closed path, if you move in one sense, you will get a positive answer. If you move in the opposite sense, you will get a negative answer. Okay. Fine. So for now, that is what is Ampere's law. We'll make use of it. Can one of you tell me what we used Gauss law for? Where was Gauss law useful to us? What did we use Gauss law to derive?
Electric flux, sir.
In some cases, flux, and in other cases,
The magnetic field due to various objects.
The electric field due to various systems of charges. Correct. So see, like there are two sides of the equation, no? Right hand side and left hand side. If you know the RHS, you can derive something on the LHS. If you know the LHS, you can derive something on the RHS. That's the idea. Okay. So in Gauss law, we had closed integral E dot dA. That's the total electric flux is equal to charge enclosed divided by epsilon naught. So if you know charge, you could tell the flux. And from that, you could tell the electric field, and reverse also. If you know the flux through a closed surface, you can tell how much charge is enclosed in it. Okay. Now in magnetism, as I said, that term closed integral B dot dl doesn't have any meaning. Okay, any significant meaning as far as your syllabus is concerned. So the only effective use we will have here of this Ampere's law is in some cases to derive the magnetic field. And in case you know this integral, you can tell how much current is enclosed. So those are the kinds of questions they can ask. Okay, so you can use Ampere's law to derive magnetic field in some cases. And sometimes if they want to ask you, they can directly ask you what is integral B dot dl over this closed loop. That integral B dot dl is not a useful quantity for now, but they'll simply ask you to calculate that quantity. Okay. Right, let us work on it a little bit. Let's solve problems based on Ampere's law. So suppose there is a random loop like this, random closed path. See, this is just an imaginary closed path. It's not like a conducting loop or a copper wire or anything. It's just a random closed path. Okay. And let's say there are some currents. Assume this current is I. This current coming out of the loop is 2I. Let's say there is another current coming out, which is 3I. Okay. Now listen, the current I is going into your screen. You can assume these as infinitely long wires. Okay. So current I is going into your screen. If current is going into your screen, consider a random point, let's say somewhere here. One of you tell me, this current I at this point, in which direction does it produce the magnetic field? In which direction does it produce the magnetic field? You can place your thumb into the screen and make your right hand fingers point towards that cross. Okay.
Sir, towards the bottom right corner of the screen.
Bottom right. Okay. So diagonal like this. Yeah. At this point, the field will be directed this way. So basically it creates magnetic fields like this, clockwise magnetic fields. Okay. The current I creates clockwise magnetic fields. It's flowing into the screen. Current is flowing into the screen. So the magnetic field around it will be clockwise. Hope the idea is clear to all of you. Then, Isha, can you tell me the kind of magnetic field or the sense of magnetic field produced by the current 2I? 2I is out of your screen. What is the sense of magnetic field produced by it? Is it clockwise or anti-clockwise? You can consider a random point somewhere here.
Anti-clockwise.
Okay. Thumb should be pointing out of the screen and fingers towards that yellow point. Then palm will be facing this way. It will produce anti-clockwise magnetic field lines like this. Okay. So I produces clockwise magnetic fields. 2I and 3I, since they are both out of the screen, they'll produce anti-clockwise magnetic fields. Okay. Now you see a closed path here. Then when you take integral B dot dl along that closed path, you have two choices. You can move anti-clockwise along that closed path. Okay, let's call that as case 1. You can even move clockwise along that closed path. Let's call it as case 2. Okay. So I want you all to calculate what is closed integral B dot dl along that loop in case 1 and in case 2. Or okay, if you are finding it confusing to do this right away, let's ignore these currents for now, 2I and 3I. Suppose I is the only current. Do integral B dot dl along the first, along that closed path in one direction and the other direction. Tell me the result. You don't actually have to integrate because you don't even know the exact shape of this path or the equation of this path. Don't try integrating. Use Ampere's law, as I said. We derived this result using a circular path for our convenience, but the result is true in general. Closed integral B dot dl over any closed path is always equal to plus or minus mu naught into current enclosed by that closed path. So use that result here. I got one answer as minus mu naught I in the first case and plus mu naught I in the second case. We'll see. Others also solve it quickly. Send your answers. Okay. Yes, she's also giving the same answer. Fine. Listen, you are taking integral B dot dl over a closed path. So the answer should either be plus mu naught I enclosed or minus mu naught I enclosed. Now this current I is clearly passing through that loop. That's the current enclosed by that loop. So it should be, the answer should be plus mu naught I or minus mu naught I. To know whether it is plus or minus, all you have to check is whether you are moving in the same sense as magnetic field or in the opposite sense. That's all. If you move in the same sense as magnetic field, dot product will be positive. Then the answer will be plus mu naught I. If you move in the opposite sense to the magnetic field produced by the current, then dot product becomes negative, the answer becomes negative. That's all. That's why I first asked you, what is the sense of the magnetic field produced by this current? This current flowing into the screen produces clockwise magnetic fields like this. Okay. So in path one, fine, you are going in the anti-clockwise direction. You are going opposite to the magnetic fields. So the answer will be minus mu naught I. That is correct. In path two, you are going in the same sense as the magnetic field. Magnetic field is clockwise. You are also moving clockwise, means dl vectors will also be aligned in the direction of magnetic field or making acute angles with it. Then this will be positive. This is also correct. Okay. Isha, is this clear? Isha, Yashmit.
Yes, sir.
Okay.
Yes, sir.
Right. Now suppose we include those two currents out of this. Okay, let's take it as a separate question. Same situation, both paths. Both possible ways of moving. You have to find out what is integral B dot dl. But now there are some extra currents, additional currents. 2I, 3I. Do this quickly, all of you. Okay, I got one answer as plus 4 mu naught I, and another for the second one minus 4 mu naught I. Fine. Listen, in this case, there are multiple currents. Okay. Some of them produce fields in the clockwise sense. Some of them produce fields in the anti-clockwise sense. Okay. But what you have to take to apply Ampere's law is the effective current crossing the loop. Okay. I enclosed here is the effective current crossing the loop. Now see, the current I is flowing into your screen. That's fine. That's like in the negative Z direction. But 2I and 3I together become 5I. They're flowing out of your screen. That's the positive Z direction. So one of you tell me, what is the net enclosed current in this loop? How much is the net enclosed current in this loop? I flowing inwards, 5I flowing outwards. What is the effective current through this loop?
4I, sir.
4I inward or outward?
Outwards, sir.
It will be outward 4I. Okay. And since the net current is outward, I can't use the word net magnetic field, but you can say that outward current anti-clockwise magnetic fields dominate on the whole. Okay, I'm not saying at every place the magnetic field is anti-clockwise. No, because if you go very close to the wire carrying current I, its clockwise field will dominate. It will dominate the fields of the other two wires. Okay, so I'm not saying the field is clockwise or anti-clockwise everywhere in space, but on the whole, if you see on average, the anti-clockwise currents will dominate because the current out of the screen is stronger. Okay. So since anti-clockwise magnetic field dominates, if you move anti-clockwise, the answer will be positive. And if you move clockwise, the answer will be negative. Therefore, in the first case, the correct answer is plus 4 mu naught I. It's effectively mu naught into net current enclosed. Net current enclosed is 4I. And for the other one, the answer will be mu naught into minus 4I or minus mu naught into 4I. Fine. Now consider something like this. Let's say there is a current I flowing into the screen and a current 2I flowing out of the screen, and you have to move along a path like this. This is also a closed path and you have to move in this sense. Okay, let me just make it clear. So just a moment. So consider this closed path and let's say you have to move this way. Now I can't call this clockwise or anti-clockwise because here it looks like clockwise, but then here it becomes anti-clockwise. So we cannot give the name clockwise or anti-clockwise to the way we are moving. Okay, but you know how we are moving. Evaluate closed integral b dot dl for that. I got one answer as 3 mu naught I. We'll see. Okay, Yash, how are you trying to answer this?
Sir, can we unwind this loop, sir?
How can you do that?
No, like it is twisted, right? So I'll just retwist it.
But that will change the way you move, no? If you unwind, then you will only be moving this way. That is not your choice. Like, see, that case and this case, I don't think they are the same. Do you think it is reasonable to do that? Is it not changing the way you move? I mean, the sense in which you move.
It is, sir.
Then you should not do that. No.
Or sir, can we consider it as two loops and do it?
But see, let us check. You gave some idea. You gave some answer also. No, your answer should be consistent with that idea. Let's see. Now this is I, this is 2I. What is the effective current?
I outwards, sir.
Effective current is I. Then the answer should be mu naught I or minus mu naught I. But you gave the answer 3 mu naught I. Okay, so this way you won't get that answer at all. And this is not the correct way to proceed. Okay. You can't change the sense in which you are moving. Okay, what was the other idea you said?
Like here, like there are two loops, right?
You want to consider it as two separate loops. Let's try it that way. That is one way of looking at it. You can take it like that. Just a moment. Let me adjust. So what you're saying is we'll take this as one loop and we'll take this as another loop. Here we are going this way and here we'll be going this way. Okay, let's call them as loop 1 and loop 2. So tell me, what will be closed integral B dot dl for loop 1?
Sir, it will be nu naught into I.
You are saying it will be mu naught into I. Okay, it's not nu, it is mu. Okay, you can't change the name. Nu is this symbol. We use it for frequency. Okay, you must have come across it in waves. In chemistry also you will use. That is nu. This is mu. Okay, it'll be mu naught I for the loop L, for the loop L1. Correct. Next.
Sir, and in L2, the current will be towards us, right? Like outwards.
Yeah, L2 2I current is outwards.
And our fingers are also curling in the direction of like the sense of like in the path with the path. So it will be mu naught into 2I.
Like you are moving in the same sense as what?
As the arrow which is given here, sir.
You are moving in that sense. Why are you saying the answer will be 2 mu naught I? Why can't it be minus 2 mu naught I? That is my question.
So the magnetic field and the DL, they are in the same direction. Right?
So yeah, you have to say that. You have to say we are moving in the same sense as the magnetic field. Anyway, first when you gave the answer for L1, you said it is mu naught I. Why are you not consider? Or okay, let's just change the question a little bit, because here I is one of the currents. I is also the net current. So we should get a clear idea what we are talking about. So for that purpose, I'm changing the question a little bit. I'll take one current as I, the other current as 5I. So Yash, what will be integral B dot dl over the first loop now?
It will be like for the it will be mu naught I, sir.
It will be mu naught I. Okay, so don't you think this 5I matters for the first loop?
No, sir.
Why not? I mean, in the formula for Ampere's law, closed integral B dot dl, what equal to mu naught I, what does I represent?
The current through the loop, sir.
Current enclosed by the loop. Okay, so if you look at it that way, 5i is not enclosed by the first loop, so it should not matter. So for the first loop, the answer should be this. Okay, correct. What is integral b dot dl over the second loop now?
Plus mu naught 5i.
Mu naught 5i. Okay, 5i is a current out of the screen. It will produce magnetic field in the anti-clockwise sense. And around 5i, we are also moving in the anti-clockwise sense. So it should be 5 mu naught I. Okay. So what is the answer now?
Six mu naught I.
Okay. So over the two loops combined, the answer should be 6 mu naught I. Okay. So the same logic using which you told the answer in the previous case, like before I changed the question, you said I plus 2i, 3i. Now you are saying I plus 5i, 6i. Okay. See, this is one way to solve. This is correct only. The answer is correct. There is another way also to look at it. We need closed integral b dot dl over this closed path, right? And there are two currents, I and 5i. What you can do is find out closed integral b dot dl only due to the current I first. Okay, I'll call this the first one or part A. Only due to the current I. Now, around the current I, effectively you are moving in the clockwise sense itself. The current is like this. And you started going this way. In between, you go wherever you want. It doesn't matter. Finally, you are coming like this. So ultimately, you are moving in the clockwise sense. And I, being a current into the screen, it produces a clockwise field itself. The field produced by I is clockwise. You are moving effectively in the clockwise sense overall, or on the whole, you are moving clockwise around that current. Therefore, due to the current I, it will be mu naught I. Next, what you will do, take only the current 5i. We'll call that as part B. So you can take the current separately instead of taking the loop separately. That way also you will get the same answer. Now around 5i, what you are effectively doing is you come like that and you go like this. You are going anti-clockwise. Okay. On the whole, around the current 5i, you are going anti-clockwise. Now current 5i being a current out of the screen, its field is also anti-clockwise. So the sense of the field and the sense in which you are moving are the same. Therefore, the integral b dot dl becomes mu naught 5i due to that current. So you add both currents now, the total integral b dot dl net. Okay. The first one was magnetic field produced by the first current. So I. The second integral was magnetic field produced by the current 5i. Now you add both net magnetic field. It will be mu naught into 6i or 6 mu naught I. Okay. You can do it this way also. Okay. So these are some questions they can ask based on Ampere's law. There are some other kinds of questions also. Let's consider this situation itself. Or, okay, fine. Let's take this first. Now, if you take a closed path, like we know the field produced by a straight current carrying wire, right? If you take a closed path around this current, which is in the same sense as the magnetic field, you know closed integral b dot dl over that complete path is mu naught into I. Okay. Suppose I ask you to take integral b dot dl only from here to here, only over half the circle. Exact path is given to you, half the circle. For this path, what will integral b dot dl be? Okay, I should not put that ring around the integral because it's not a closed path now. It's an open path. But if I do integral b dot dl over a semicircle around this wire, what will integral B dot dl become? Think about it, type your answers in chat.
Sir, can you repeat the question once again?
Instead of taking the full circular path, what if we move only along half the circle? Okay, from one side of the wire to the exact opposite side of the wire. So we are moving along that semicircle. So along that semicircular path, what will integral B dot dl be? I got two answers as 0. We'll see. Isha, any answer? Okay, the ones who gave answers as 0, can you explain why you said it is 0?
So this is Ampere's law, right? So Ampere's law is
This is
defined
not
for
Ampere's law. I didn't ask you to use Ampere's law. No, I'm asking what will integral B dot dl be for this path? Don't use Ampere's law if you don't want to use, if it doesn't match the requirements.
then sir it will be 0 because I enclosed is 0.
Where do you have a formula for open paths like this? Where did you learn that for an open path it depends on I enclosed? For an open path, I enclosed, the term itself doesn't make sense. Okay. Closed path can enclose something. How can an open path enclose something? Think from the fundamentals. Anugraha, on what basis did you say 0?
Ampere's law, sir.
Ampere's law is applicable for closed paths. The path given to you is not a closed path. Okay. We just, in this class itself, we derived this result. We literally derived this for a straight wire moving along a circular path around it. What did we do there? We visualized the magnetic field first. Then we visualized dl. We understood that B and dl were in the same direction, so the dot product becomes B dl. Then we substituted the formula for the magnetic field dl. We did all that. Then we finally got mu naught I. If you integrate dl over the complete path, you got mu naught I. Now I am asking you to integrate dl only over half the path. What will the result be? Clearly, we wrote integral dl as 2 pi x. If you move only along half the path, what will you write integral dl as for the semicircle?
Pi x.
Pi x, then what will the result become?
Mu naught I by 2.
Mu naught I by 2. Okay. You could have answered it based on symmetry also. If you move along the complete circle, it is mu naught I. You know the answer is mu naught I. And see, whatever magnetic fields exist over one semicircle, the same pattern of magnetic field exists over the other semicircle also. So how much ever is integral B dot dl over this path should be the same as integral B dot dl over the other path, over the remaining path. I'll draw that in yellow. The pink one and the yellow one should have the same values of mu naught I. I mean, not mu naught I, sorry. Should have the same values of integral B dot dl. So because the fields you see on this side are same as the fields you see on that side. The distance you are moving this side is same as the distance you are moving that side. Then the integral on this side should be same as integral on that side. You know, total integral is mu naught I. Then half of it should be mu naught I by 2. You could have answered that way also. So in case it's not a closed path, obviously you have no choice. You can't use Ampere's law. You have to fall back on the basics. Okay. And this point is exactly what they tested in this year's JEE Advanced. I'm not saying they asked the exact same question, but they tested if students can integrate b.dl over an open path. Okay, they gave a much more complicated system, not as easy as this. But see, generally, you will learn some formulas. If the given situation doesn't satisfy the conditions of that formula, then you will have to think on the basis of fundamentals. That's why derivations are very important. That's why you need to know how you got every result, every formula. Okay. Fine, let's try another question. Suppose there is a square path like this. It's a closed path, fine, but okay. Fine, I should not have, no, I should not say square path. Let it be. Suppose there's a current. Let's place the current. Where shall we place it? Okay. Just a moment. Let's say there's a current carrying wire here. The current is I, and where is the wire? Okay. Let's say it is at a by 2 root 3, comma 0. So current is in the z direction, negative z direction. It cuts the x-axis at that point. I want you to find out integral b dot dl over a path like this. Let's say this is point A. Its coordinates are a root 3 by 2 comma 0. And from there you go to point B, whose coordinates are, I think you can guess it, 0 comma a by 2. Along that path, I want you all to find out closed, okay, not closed, it's not a closed path. I want you all to find out integral b dot dl. The magnetic field is produced by this current. Try. The hint is in the coordinates actually. Any idea, anyone? Okay, one of you tell me, the previous question also, it was not a closed path. The path was from here to here. What was the idea we used to derive the integral b dot dl in this case? Just tell me how we solved the previous question.
So we just calculated like how much distance we moved.
So we actually did integral b dot dl, right? Because this was a convenient case actually, because the straight current carrying wire produces circular field lines and you are moving along the circle. So that way it was convenient in a way that, I mean, how exactly was it convenient? Because the field strength everywhere on that path is the same. Whether you complete the circle or you take only some part of the circle, the field strength was same everywhere. So we made use of the integral that we already had in our hand. We just changed the limits of integration. Okay. Here, the path given to you is a straight path. The current is a straight infinite current. It's into the screen. Into the screen, it produces magnetic field lines like this. It produces circular magnetic field lines. Okay. Not exactly like this, but somewhat like this. And the line along which you are moving is a straight path. So that is what makes this case complicated. Then can you solve it using integral b dot dl? Like in this case, if you visualize the magnetic fields produced by this current at different points, the dl vector will be making different angles with the magnetic field. It becomes too complicated even if you try to integrate. Okay, at some points, like maybe here at the shortest point, nearest point, the angle between dl vector and magnetic field is this way. It will be 180 degrees. At different points, you'll have different angles. So integral b dot dl, that b dot dl dot product itself is difficult to evaluate. So any other idea? We can't literally do integral b dot dl in this case because magnetic field will vary from point to point, because different points on this line are at different points from are at different distances from the current. So writing an expression for the magnetic field itself becomes complicated. Then taking dot product with dl and then integrating that on top of it, not possible to do. Okay. So there must be some other intelligent way to solve. Yes, you gave some answer. How did you solve this? How did you arrive at that answer?
No, sir, it is wrong actually. I just calculated the length of that hypotenuse and I multiplied it.
That you cannot do, no? If
Yes,
that length was along the magnetic field line, then that's fine. But we are not moving along the magnetic field now. So that won't work. Any other ideas, anyone? What was the other idea I told you to solve this question? Not just adjusting the limits. What was the other idea I told you to solve this question? Anyone?
For full loop, it was mu naught I, so for half, it would be mu naught I by 2.
Okay. For the complete loop, the answer is mu naught I. For half of the loop, it should be mu naught I by 2. But see, it doesn't mean that for every loop over half of it will be mu naught I by 2. For example, had the loop been asymmetric, like in this case you take. We know here, okay, I'll mark some points in green. At these points, the magnetic fields are strong because they are close to the wire. Okay. I'll mark some points in red. At these points, the magnetic fields are weak because they are far from the wire. So now if you do integral b dot dl over, let's say 5 centimeters here and 5 centimeters here, will the result be same? if you do integral B dot dl over a certain length on that side and over the same length on this side, will the integrals be same? That's the question.
No, sir.
They will not be same because the field is not same there and here. So there's no guarantee that the integral will be same. In case of circular path, it will be same because everywhere on that circle, the field is the same. Okay. So for full circle, if it is mu naught I, then for half circle, you can say it is mu naught I by 2 for sure. Okay. But if the field is non-uniform, then you cannot comment on it. I mean, you need some other information. Okay. Directly you cannot tell. Now here we have that problem. Okay. And also for circle, we know the answer we used, but okay. Yeah. For full circle, it was mu naught I. So for half circle, we could say it is mu naught I by 2. Is the answer mu naught I only valid for circular loops or for any loop? What if you had a loop of this shape? This is all outside your screen and that part is behind your screen. Will it still be mu naught I for that loop or not if it is enclosing that current?
Yes, sir.
It will be, okay. For Ampere's law, all you need to know, I mean, all you need to confirm is whether it's a closed loop or not. You don't need to bother about the shape of the loop. Okay, for any closed path, it's correct. I told you before also, we are deriving for a circular path, but the result is true for any closed path. Okay. Then that's the only idea we are left with. We have to imagine a closed path of which the given path is a part. And you have to imagine a closed path in such a way that it becomes easy for you to integrate this somehow. Okay. Let me give you another situation where I think you will come up with an answer. Then we'll come back to this. Consider a wire, but okay, wait, we don't need all this. Just a moment. We'll just take the coordinates. Consider the coordinate system like this. Assume current is passing exactly along the z-axis. Current is I. And you are given a path from here to here. What are the coordinates? A by 2, comma A by 2. Two, x coordinate A by 2, y coordinate minus A by 2. Can you try to integrate B dot dl over this path? Or do you have any idea to integrate this? It's a straight path from A by 2 to A by 2 minus A by 2.
Sir, can we consider a square and then
Correct.
find the
Correct. So this side, this line that is given to you can be imagined to be part of a square at whose center this wire lies, at whose center this current I is passing. So you imagine a square like this, square path. Square path is a closed path. You can apply Ampere's law and you can tell the result for that closed path, complete closed path. So for the complete closed path, integral B dot dl is mu naught I. But you were not asked for the complete closed path. You are asked only for one side of it. What will the answer be?
mu naught I by 4.
1/4 of it. How are you sure that it's exactly 1/4?
Property of square.
Symmetry. Okay. Like you see different points of this side. There are different distances. That's fine. So different magnetic fields will be there. But for the other sides also, the same pattern of distances is there. The same pattern of magnetic fields is there. Okay. So integral B dot dl should be same for each side, for all the sides. Okay. And for all sides combined, we know it is mu naught I. Then for one side, it should be exactly 1/4 of that, mu naught I by 4. Okay. So in some cases, even if the path is not closed, you can do integral B dot dl. Now you take this for practice, solve it on your own. And effectively, yeah, that is all you need to know about Ampere's law. So practice some problems based on this. And yeah, I'll send you a worksheet where you'll have to solve, where you'll have to derive magnetic fields produced by current carrying wires inside the wire, outside the wire, cylindrical wires. Okay. It's important for board examples. It's there in your textbook also in applications of Ampere's law. We'll do that. And in some cases, we can use Ampere's law to derive magnetic field. Just like we use Gauss law to derive electric field, we can use Ampere's law to derive magnetic field. Some cases like that we'll discuss in the next class, and then move on to the other part of this chapter, which is motion of a charge in a magnetic field. Okay. Till now we have discussed the magnetic field which currents produce. Okay. You can derive it either using Biot-Savart law, or now you learned that you can derive it using Ampere's law. Like Ampere's law involves the term magnetic field. We still didn't make use of it to derive the magnetic field, but it can be done. That we'll learn in the next class. After that, the rest of the chapter is about what happens to a charge which moves in a magnetic field. Okay, what kind of forces it experiences, how it moves and all. So, okay. So I'll send you a worksheet with some questions, this 5th question and some other questions also, which are based on application of Ampere's law. Solve those questions. Okay, thank you all. I'm closing this session.